Good morning, everyone. Mathematics is the language of science. Every scientist and researcher in any field of knowledge will be knowing the importance of mathematics as it is the principal tool to explain, prove, and predict the phenomena in nature and to solve the problems and to develop new systems in science and technology. The mathematics community of India feel very proud that we have plenty of great mathematicians including Sir Srinivasa Ramanujan, Madhava, R.C. Bose, Shrikhande, etc. The great Indian mathematician Sharatchandra Shankar Shrikhande passed away last month on 21st April 2020 at the age of 102. As you all know, he was known as an Euler's spoiler as he, together with R.C. Bose and E.T. Parker, disproved the famous Euler's conjecture proposed long back in 1782. Mathematics and statistics people will also be familiar with Shrikhande graph, which is used in statistical design theory. Today, Aquinas College is arranging a memorial lecture and we have very eminent person to talk about him, who is none other than Dr. A. Vijayakumar, the famous graph theorist who doesn't need an introduction as he is such a popular, great person, which is very evident from the number of registrations we received for this webinar itself. He is a retired professor of CUSAT, now working as Emeritus professor there. He has visited several countries and attended the ICMs held in Spain, Korea, etc. He is the Vice President of Ramanujan Mathematical Society. We have a surprise awaiting for us that Dr. Mohan S. Shrikhande, another mathematical genius, retired from Central Michigan University and son of the great legend S.S. Shrikhande, joining us online live from US during this webinar. I feel privileged to welcome Dr. Mohan and Dr. Vijayakumar for sharing their wonderful thoughts with us. And I heartily welcome each and every one of you to the webinar on SS Shrikhande, a tribute to an Euler's spoiler. Now let us hear an introductory note from Dr. Mohan S. Shrikhande. Over to you, sir.
Yes, I would like to thank Aquinas College Mathematics Department for arranging this webinar. I would also like to thank Professor Vijayakumar for giving me the opportunity to speak a few words about my father, S.S. Shrikhande, who passed away on April 21st, 2020. Since Professor Vijayakumar is giving his talk on S.S. Shrikhande life and work, I will confine myself to recalling some personal memories from 1958 when my mother brought me and my two brothers and a sister from Nagpur to Chapel Hill, North Carolina in USA. We all came there to join my father, who had come a few months earlier to teach and do research work with Professor Rajchandra Bose. My father was Professor Bose's first PhD student and had completed his thesis in 1950. In Chapel Hill in 1958, I was just a youngster, 13 years old, and was in middle school. I had no inkling about what exactly doing research and teaching meant. I only remember that my father used to walk from our apartment to his office daily early in the morning and come home in the evening. Later on, I realized that he loved to walk and used to walk about 4 or 5 miles daily until his late 80s. I remember one day while in school, when I was going from one classroom to the other, my teacher met me on the staircase. She asked me how I was doing and whether I had read that day's New York Times. I said that I had not. In fact, I don't think we subscribed at that time to that particular newspaper. Well, she told me that be sure to get hold of the paper because my father's photo was on the front page. I remembered later that my father had gone to New York for a mathematics meeting, and apparently some big news took place there. I recall that the New York Times front page photo was a picture of my father, Professor Bose, and E.P. Parker writing some things on a big blackboard. The three people came to be known as Euler's spoilers, who had disproved an old conjecture of Euler. I didn't know at that time what the big fuss was. So I didn't know what the big fuss was all about, but I was very happy that his picture had appeared in a famous newspaper. Much later, after I grew up and got my PhD in mathematics, I came to realize the true significance of Euler's conjecture and what it meant to have a father who was one of Euler's spoilers. I think that's it. Thank you very much for your attention.
Okay, sir. Thank you very much. I think now we can move to the presentation of Vijayakumar sir.
Okay.
Is it okay, sir? Right? Okay.
Yes.
Okay.
Okay.
Okay. Okay. So, Vijayakumar sir, can you join us?
Okay. So I'm from Cochin University of Science. I have been teaching for 2 years. I retired 2 years ago, and currently I'm Emeritus Professor in the Department of Mathematics, CUSAT. Good morning to you all and namaste all participants. Let me first of all thank the Aquinas College, Edakochi, for arranging this webinar in memory of legendary mathematician Professor Shrikhande and inviting me to speak on him. Happy to inform you that the Principal College, Mrs. Bridget Gigi, and HOD of Mathematics, Sita Paul, were both my students in Cochin University. Thank you all for having me. This college is associated with the Diocese of Cochin, with which I have a very long association through a unique project called Cochin Olympiad, for which I am a core team member. This Cochin Olympiad project imparts quality education and total quality of socially backward children of Cochin Diocese. Any discussion on the three Euler's spoilers should begin with an exposition of Euler in orthogonal Latin squares.
So one second, sir. 1 second. Your audio is slightly breaking. So 1 second. So your audio is slightly breaking. So can you do something? Just make your microphone closer to your mouth or something. Is it audible?
Is it okay now?
Now it's okay. Now it's okay.
Okay. Any discussion on three spoilers should begin with an exposition of Euler's work in orthogonal Latin squares and graph theory. You should that the strongly graphs is mainly due to R.C. Bose, Professor Shrikhande during 1903. In the present day, researchers may not have heard on the exciting contributions of them. It is high time that their work is popularized, strongly feel that we should celebrate Shrikhande's birthday, 19th October, as National Graph Theory Day. I am happy that Professor Mohan Shrikhande of Central Michigan University and Professor Arun Mukti both, a close associate of Shrikhande, have joined this webinar. Very close to the works of Shrikhande, so any mistake or in the timeline of his works may kindly be corrected offline. In all the webinars that I have been giving since lockdown, I have been highlighting the need for interdisciplinary research in mainly due to the knowledge explosion. Works of R.C. Bose and Shrikhande together several branches of knowledge such as partial geometry, design theory, field theory, graph theory, statistics, computer science, and so on. They have three parts. First one, Euler and his outstanding contributions, a timeline of Shrikhande. Second part, Euler's conjecture on mutually orthogonal Latin squares and Euler's spoilers. And third part will focus on the Shrikhande graph. So we will pay homage to the great inspiring teacher, APJ Abdul Kalam, with whom I had a very close association, who passed away on 27th July 2015. There are several quotes, and the quote that which I have taken today is, don't take rest after your first victory, because if you fail in second, more lips are waiting to say that your first victory was just a luck. So keep on running and don't take rest. This is dedicated to my guru, Professor Basir Hasan Abdi, who was the founder, head of the Department of Mathematics in Cochin University, and who was my mentor, friend, philosopher, and guide. He is basically and in 1990, and are organizing in our memorial for the last 20 years. From Aquinas College, Cochin, Kerala. So, Shrikhande was born on 19th October 1917 and passed away on 21st April 2020 around 8 p.m. in the night. This is Sri Sarachandra Shrikhande, the collection of photos that I have. Okay. Any discussion on Shrikhande should start with Euler's contribution. Euler also was born in April 15th and passed 18th September 17. R.C. Bose was born on 19th June 1901 and passed away on 31/10/1987. On the left, a brief of R.C. Bose, best known for his work in design theory and the theory of error correcting codes. You know, BCH codes is Bose-Chowdhury-Hockenham code, which is a 2 error correcting code. He mostly worked in Indian Statistical Institute, Calcutta. Coming to Leonhard Euler, his advisor was John Bernoulli of the great Bernoulli family. I'll talk about Bernoulli family in detail later. His son, Johann Albrecht Euler, was also a professor of mathematics. Euler was totally blind. If you Google blind mathematician, you'll be surprised to see a long list, and Euler is one of them. Euler lost his right eye in 1738 and the left eye in 1766. Years. But on a convenient date, 15th December 2007. So I will be showing some of the slides which I had presented then, obviously focusing on Euler. Leonhard Euler, as you know, is popularly known in mathematics circle as the analysis incarnate, the avatar of analysis. He was totally blind. This is the family tree of Bernoulli's family, which were ruling the science scenario for about 2 centuries. All of them are based at Bâle, Switzerland, starting from Nicolas Bernoulli, ending with Jacob Bernoulli II, for a period from 1623 to 1780. What is interesting is on the right side, you see the Leonhard Euler. Euler does not belong to the Bernoulli family as such, but Bernoulli family considered him as a spiritual son of Johann Bernoulli. That's why in the genealogy chart you find Leonhard Euler. So Leonhard Euler was blessed to have such a scientific background of great scientists, about 120 of them, most of them very outstanding. You know, in 1988, the British mathematics educator asked the mathematical community to list most beautiful theorems. There was a tie second place between the polyhedral formula, which is B minus E plus F is equal to 2, number of vertices minus number of edges plus number of faces in any polyhedron is 2. In general, is 2 minus 2g, where genus of the surface, g. And Euclid's second theorem, that there are infinite number of primes. Okay, so Euler were and you were ranked 2. And undoubtedly, the face went to the magic equation of Euler, e raised to I pi plus 1 is equal to 0. In fact, Richard Feynman, the famous physicist Nobel laureate, the Euler as the most remarkable formula in mathematics. I have a request to the participants. It will be a kind gesture if you can list down, according to you, best 10 theorems in mathematics, and you can send me. Consider the best. They are calculated without effort, just as men as eagles sustain themselves in the air. So calculation was so simple for him, the effort. He introduced the concept of a function and notation for trigonometry, the letter E, the letter sigma for summation, and the Greek letter pi to deal with circles. Okay, we will come to the slide on the birth of graph theory. Graph theory was born on 1736 as a solution of a problem relating to the geometry of position. Geometry of position is geometria situs in Greek language, which means graph theory. And you know, analysis situs means topology. So graph theory originated with a paper presentation by Euler in the St. Peter's Academy and proved that the Königsberg bridge problem cannot have a solution because of the conditions on the degree of the vertices. Another contribution of Euler is, in fact, Fermat, the famous French mathematician, conjectured that Fn is equal to 2 raised to 2 raised to n plus 1. They give a formula for all primes. In fact, f of 0 is 3, Fn 5, F2 17, and F4 6, 5, 5, 3, 7, they are all primes. But Euler disproved this conjecture in 1732 and proved that F5, that is 2 raised to 2 raised to 5 plus 1, admits a prime factorization as 641 into 6700417. So Euler's conjecture is disproved, Fermat's conjecture is disproved by a simple counterexample by Euler. So there are only 5 Fermat primes obtained by substituting n is equal to 0, 1, 2, 3, and 4 in Fn is equal to 2 raised to 2 raised to n plus 1. In fact, both the factors of F5 are primes. Nowadays, such composites are called RSA composites, a terminology in cryptography. Euler has contributed a lot to theory of equations, number theory, differential geometry, calculus of variations, mechanics, theory of ships, music theory, and so on. To be frank, without Euler, there was no branch of mathematics to a particular stage. Okay, so I have a suggestion for 3 websites to know more about Euler. All of them are containing several information about the works of Euler, and you will be surprised to know that even now Euler's works have been edited and published by the Euler's Archive and Euler Society. I will also thank my good friend Robin Wilson, who is currently Emeritus Professor in the British Open University, who has visited Cochin at least 3-4 times. Look at his picture. He is wearing the dress of like Euler and giving a lecture on Euler. Yes, he's a great man in the sense that whenever I had any doubt on the history of mathematics or history of graph theory in particular, he was very patient enough to immediately tell me, even now, even after some 20 years of acquaintance, he has been keeping in touch with me. A big salute to Robin. Okay, now let me come to the Shrikhande's timeline. As you all know now, Sarat Chandra Shankar Shrikhande was born on 19th October 1917 at Sagar, Madhya Pradesh. His wife Shakuntala passed away in 1988. He has 2 sons and 1 daughter, Mohan Shrikhande, who is currently present here, and Anil Shrikhande, and 1 daughter, Asha. He took his BSc honors from Government College of Science, Nagpur University in 1942. You know, Madhya Pradesh is at the center of India almost, and you will see Sagar. Sagar is here, and that's where he was born. So he contributed a lot to combinatorics, design theory, and graph theory. He took his PhD as the first student of R.C. Bose in 1950 from University of North Carolina, Chapel Hill. From 1951 to 53, he was in University of Kansas, and worked in Banaras Hindu University, University of Bombay for a long time, and also worked as director of the Mehta Research Institute, Allahabad. He has 3 PhD students, Vasanthi Bhatnaik, who is no more, who was head of the Department of Mathematics for a long time in Bombay University, and Bhagavan Das, and Professor Naveen Singhi, who was working as a professor in Tata Institute of Fundamental Research in Mumbai. So these are photos of Shrikhande at the younger days. Okay. Now let me come to the real problem of Euler's problem of 36 offices. I'll be very slow so that you will understand what is the problem and also try to understand what is the difficulty in solving it and how great Shrikhande's work was. The problem was simple looking as usual. There are plenty of problems in mathematics which are quite challenging, but statement is very, very simple looking. And Euler's problem belonged to one of them. To arrange the Euler's problem of 36 offices is to arrange 36 offices from 6 different regiments of 6 different ranks in a 6x6 array so that each row and each column contained 1 officer of each rank and 1 officer of each regiment. Hope the problem is clear. I have to arrange 36 officers in a 6x6 array. That array is popularly now known as Latin square, so that each row and each column contain 1 officer of 1 rank and 1 officer of each regiment. So there should not be any repetition of the coordinates. That's what precisely it says. Suppose there were only 16 officers. Suppose on the left, I see arrange the regiments 1, 2, 3, 4, 2, 1, 4, 3, 3, 4, 1, 2, 1, 4, 3, 2, 1. And on the right, arrange the officers in the order 1, 2, 3, 4, 3, 4, 1, 2, 4, 3, 2, 1, and 2, 1, 4, 3. And if I superimpose them, you know, there is no repetition of the coordinates. So each column and each row will have distinct elements. So what I wanted to tell you was simply that Euler's problem of 16 officers, if had it been, could be easily solved by this, and there are many other possible combinations also. So the journey of the Euler's conjecture started in 1788 and ended in 1959, as you all know, passing through about 177 years. So this is the pattern of arranging a 4x4 mutually orthogonal Latin square of order 4. This is an article which I wrote in Malayalam newspaper, Malayalam Manorama, in a couple of years back, I think 11 years ago, on 36 officers problem. You see the picture of Euler, R.C. Bose, and Shrikhande. Yeah, I could read now that this was when Shrikhande was 92. So, what is a Latin square? A Latin square of order n is an n by n array with entries from the symbol 1, 2, 3, etc. n, such that each symbol occurs once in each row and in each column. So this is a type of matrix. This condition is not there for a matrix. The entries can be repeated. But in a Latin square, so it's a special type of a matrix where each symbol occurs once in each row and in each column. So every matrix is not a Latin square, but every Latin square is a matrix. How many Latin squares of order n is a good question. We can see that the number of Latin squares of order n is n factorial into n minus 1 factorial into n minus 2 factorial, etc. 1. So it's going to be a huge number. In fact, it's quite simple to know that for every positive integer n, there is a Latin square of order n. What you have to do is simply take the multiplication table of a finite group of order n. You fix at the eighth row and bth column, you put A star B, and all these A star B's are going to be distinct. So you get an example of a Latin square. Obviously, all Latin squares cannot come as the multiplication table of a finite group of order n. Okay. I say that two Latin squares of order n are distinct if they are distinct as matrices, that is, the elements differ in at least one position. Now let Ln denote the total number of distinct Latin squares of order n. Okay. Now I need one more terminology, a reduced Latin square. A Latin square of order n with entries from 0, 1, 2, 3, etc. n minus 1 is reduced if both the first row and first column are in the standard order of 0, 1, 2, 3, etc. n minus 1. So if you take a 3 by 3 Latin square, it is reduced if I start with 0, 1, 2 as the first row and 0, 1, 2 in the first column. Okay, let us denote by Gn the number of reduced Latin squares of order n. There is a theorem which says that for each n greater than or equal to 2, the number of Latin squares of order n is equal to n factorial into n minus 1 factorial into number of reduced Latin squares of order n g of n. Mathematician X in 1994 proved that L of 10 is, is a huge number, 10 factorial into 9 factorial into that huge number. By probabilistic method, you can prove that G15 is equal to 1.5 into 10 raised to 86. The number of visible atoms in the universe is 4 into 10 raised to 78. And number of reduced Latin squares of order n is G15 is 1.5 into 10 raised to 86, which is much, much more than the number of visible atoms. So you take an atom, as a joke, I will say, you take an atom and put it in a Latin square, and another atom in another Latin square, number of Latin squares will be more. That's what it means. Okay. We'll come to the definition of a mutually orthogonal Latin squares. It's also called Greco-Latin squares due to Euler, because he was using Greek alphabet in one of the Latin squares and Latin alphabet in the other square. Okay. So two Latin squares A and B are mutually orthogonal Latin squares if, when superimposed, each element appears exactly once. So there is no repetition of the coordinate elements. So when you know the definition of a mutually orthogonal Latin square, which I suppose it is clear to you, when you superimpose two Latin squares, each element should appear only exactly once. So the problem of 36 officers can be translated into problem of mutually orthogonal Latin squares is construct a pair of mutually orthogonal Latin squares of order 6. Unfortunately, Euler failed to solve this problem of constructing mutually orthogonal Latin squares of order 6. But before that, let us think about for which values of n MOL exist. For example, if you take n is equal to 2, you see the only 2 by 2 Latin squares are 0, 1, 1, 0 and 1, 0, 0, 1. I suppose you agree with that. So if you superimpose, this is not an MOL because the coordinates 0, 1 and also 1, 0 are repeated in the second row. Right. So there is no pair of mutually orthogonal Latin square of order 2. But when you take n is equal to 3, yes. If you take 2, 1, 0, 0, 2, 1 and 1, 0, 2 and 1, 2, 0, 2, 0, 1 and 0, 1, 2, if you superimpose, each entry appears exactly in one column and each entry in each row, exactly once in each row. So for n is equal to 3, there exists a pair of mutually orthogonal Latin square of order 3. Now, look at n of n, the maximum possible number of mutually orthogonal Latin squares of order n. See, I am slowly trying to convince you how hard the conjecture was and how strong Shrikhande, Bose and Parker were to solve this problem negatively. Okay, there is a theorem that for each n greater than or equal to 2, the number of possible number of MOLs of order n is bounded above by n minus 1 and it is minimum is 6 for all n greater than 6. So upper bound is more significant and you can see that when n is a power of prime like 8, 16, 32, etc., 9, etc., upper bound is achieved. So very hard research problem is find a formula for the maximum possible number of mutually orthogonal Latin squares of order n. That is, find a formula for n of n. Suppose n of n is equal to n minus 1. They say that it is a complete set of MOLs and a complete set of mutually orthogonal Latin squares is equivalent to a finite projective plane of order n. See, the problem gets translated or transferred from one domain to another. That is the beauty of doing mathematics. You find a problem in one area of research, you can simply translate to another area of research and try to solve it there. So now you should know what is a finite projective plane, just like you have an example of a finite field. For example, you know finite field exists if and only if the order is prime or prime power. Right? Fine. So this is the smallest finite projective plane. This is popularly called the Fano plane. Each line has 3 points and 3 lines, 7 points and 7 lines. Okay, the 7th line is circular in shape. Only axiomatically a line should satisfy that it contains some points. So here n is equal to 2. So there are n square plus n plus 1, which is 7 points, and n square plus n plus 1 lines, 7 lines in the Fano plane. So this is the smallest finite projective plane, and that is of order 2. You can shift from Fano plane and finite projective plane to the notion of a Levy graph, which I am not going to concentrate. Those who are interested, you can translate the language of Fano planes to Levy graph. You can refer to Wikipedia and get more information. Okay, there is a prime power conjecture. But before that, there is a more R.C. Bose theorem, which gives only one-way implication. Suppose you take a prime power, say 3 square, 9. The set of polynomials of the form f of xy is equal to ax plus y, where a is not 0, in the finite field of order n, represents a complete set of n minus 1 MOLs of order n. Let us spend 1 minute. See, what does this theorem say now? That gives me a method to construct a complete set of n minus 1 mutually orthogonal Latin squares of order n using a polynomial from a field Fn, with the coefficients from field Fn. What is celebrated prime power conjecture is, which is still open, there exists a complete set of mutually orthogonal Latin square of order n, if and only if n is a prime power. So one-way implication is more R.C. Bose theorem, and the other way implication is the tricky part, which remains as a conjecture. So suppose, for example, I want to construct a complete set of 3 mutually orthogonal Latin squares of order 4. I require a finite field of order 4, F4. You know how to construct finite fields of prime power. Okay, ZP, that is integer modulo P, gives me a field if and only if P is prime. To construct a field of order 8, say for example 2 cube 8 or 9, which is 3 square, I have to use a finite field of order 4 and take the irreducible polynomial over F2. So you take the irreducible polynomial as x square plus x plus 1, and if alpha is the root of this equation, the elements are 0, 1, alpha, alpha square. So for convenience, I have used the symbol 0, 1, 2, 3. Okay, so I gave an example of a complete set of 3 mutually orthogonal Latin squares of order 4. You see here Shrikhande and R.C. Bose writing down some irreducible polynomial and roots of this polynomial and trying to get hopefully a complete set of mutually orthogonal Latin square. I would suggest all beginners to read these 2 books, Discrete Mathematics using Latin squares and Course in Combinatorials. Now comes the Euler's conjecture. See, for 2, n is equal to 2, there is no pair of mutually orthogonal Latin square of order 2. For n is equal to 6, which is the famous 36 offices problem, Euler could not solve Euler's 36 offices problem. And next come is 10, which is an odd multiple of 2. And for 10, also he was unable to construct a pair of MOLs. So these observations motivated Euler to conjecture that if n is an odd multiple of 2, there is no pair of mutually orthogonal Latin squares of order n. What was the reason? For n is equal to 2, there is no. N is equal to 6, he could not. And n is equal to 10, also he could not. Therefore, he made a conjecture that if n is 2 times 2k plus 1 for k greater than or equal to n, then this maximum number of mutually orthogonal Latin square is going to be just 1. There cannot be a pair. Look at a brief historical survey. In Tari in 1900, proved that N6 is 1. So, thought that Euler's conjecture may be correct. They are going to give you a surprise. Again, Tari's result gave a wrong direction in thinking that Euler's conjecture could be correct. Parker proved that n of 21 is greater than or equal to 4, and n of 10 is greater than or equal to 2. So, 2 Latin squares of order 6 does not exist was shown by Tari in 1900, Fisher and Yates in 1934, Yamamoto in 1954, Douglas Stinson in 1984, and a coding theoretic solution to 36 offices problem is available, and also a linear programming based proof on non-existence of a pair of mutually orthogonal Latin squares of order 6 comparatively recently in 2004. Let me stress this point. The problem started as a problem of, it's not a problem, it started as a puzzle. Suddenly it became a problem, and now mathematicians are trying to get the proof of those things using very different method. This is also a unique culture of mathematics, trying to attack a problem in so many different ways. So a great breakthrough happened in an AMS meeting in 1959. R.C. Bose, S.S. Shrikhande, and E.T. Parker proved that there exist pairs of n by n Latin squares of all n except n is equal to 2 and 6. That's why. So what did they do? They simply totally attacked, shattered the hope of Euler that disproved the conjecture of Euler. That is, n of n is greater than or equal to 2 for all n except 2 and 6. That was a wonderful contribution of Bose, Shrikhande, and Parker, which appeared in Transactions of American Mathematical Society in 1960 and the Canadian Journal of Mathematics in 1960 again, in 2 different parts, on the further results on the construction of mutually orthogonal Latin squares and the falsity of Euler's conjecture. So as usual, New York Times, April 27, 1959, carried an editorial in its Sunday magazine about the recognition of the significance of the recent disproof of a famous conjecture concerning Latin squares made by Euler in 1780. Here I want to share a personal information. When I went to International Congress on Mathematics Education in Mexico, quite a years back, I told about the contribution of Shrikhande Bose, which appeared in a newspaper. I was talking about the popularization of mathematics through print media and so on. This happened about 12 years back. So when I mentioned that it was the name of two Indians and Parker, which came to print for the first time in the history of mathematics, they said, no, we don't agree. I think it should be the four-color problem or Fermat's last theorem and so on. But we can be proud, as far as I know, somebody can correct me, as far as I know, that this is the first editorial or first information in any newspaper, and that belongs to us, that of Park. This is precisely the New York Times paper, and this was what Mohan was mentioning in his introductory remarks. R.C. Bose, E.T. Parker is Ernest Tilden Parker. Parker also passed away in 91, and which was leaving only Shrikhande till this year. Bose, Ernie, that is E.T. Parker, and I, Shrikhande said later, had the rare privilege of seeing our works reported on the front page of the Sunday edition of the New York Times, April 26, 1959. And as everyone knows now, and why you also know, three of them are now known as, among their colleagues, as Euler's spoilers. So as a disclaimer, this quotation, I got it from Nityananda Rao's article on Shrikhande, which appeared in a nice mathematics magazine published by Professor C.S. Aravinda, Indian Institute of Science, October issue of 2017. Fine. So this is the photo which I showed earlier in the newspaper, end of the Euler's conjecture. Now you know why Shrikhande is popularly known as Euler's spoiler, and what was the difficulty of the problem, and the problem is being attacked even now. That is still even 2004, there were approaches to solve 36 officers problem using linear programming method. So I'm reaching to the last part of my lecture. It will take 10 minutes. So we'll be able to wind up my lecture by 12:15. And this will be followed by a video film on Shrikhande by Professor Arun Muktiboth. So this is the beautiful thing. I'll tell you how Shrikhande graph was evolved as a consequence of a theorem. This is beautiful because it is symmetric. It is vertex symmetric. It is regular as well as symmetric. I feel that beauty is a consequence of symmetry. You can debate on it. So symmetric pictures are all beautiful. Beautiful pictures are all symmetric. I don't know. You can discuss about that. Okay. I quote from my friend Saras Sane, the Shrikhande graph, which appeared in a science popular magazine, Resonance, Science Education magazine, October 2015. Questions in mathematical statistics led to the discovery of some elegant mathematical structures, and the Shrikhande graph is a beautiful example of this. There is a joke, because we should cut some jokes also, not only jokes, but this joke is very famous. You know, P.C. Mahalanobis, who was the founder of the Indian Statistical Institute, wanted R.C. Bose to visit paddy fields and advise him on sampling problems for the estimation of yield of paddy. But Bose, being a theoretician, did not like the idea of going to paddy fields, but he was working on combinatorial problems using Galois fields. So the workers of the ISI used to make a joke about this. So whenever P.C. Mahalanobis asked about Bose, his secretary would say that Bose is working in fields, which was caused confusion for P.C. Mahalanobis. In fact, it was not paddy field, it was actually Galois field, because all the theory Bose and Shrikhande invented when Bose was in Indian Statistical Institute. Okay. So we'll come to strongly irregular graph. This is the main point which I want to discuss. A strongly regular graph with parameters n, k, lambda, mu is a graph with the following properties. I shall be slow. I need only 15 minutes. N, k, lambda, mu is a graph with the following properties. There are n vertices. Each vertex is of degree k. That means a regular graph of degree k. And any two adjacent vertices have lambda common neighbors. And any two non-adjacent vertices will have mu common neighbors. So two adjacent vertices will have lambda common neighbors, and any two non-adjacent vertices will have mu common neighbors. So n, k, lambda, mu. And the Shrikhande graph turns out to be a strongly regular graph of order 16. Regularity is 6. Lambda is 2 and mu is 2. The equality of lambda and mu I will discuss later. It says something else. Now, 16 vertices, 6 regular graph will have 48 edges, right? 16 into 6 by 2. So it's a graph with 16 vertices, 48 edges, the regularity is 6, lambda 2, mu 2. Let us get some examples of strongly regular graph. Your strongly regular graph with parameters 10, 3, 0, 1. Hoffman-Singleton graph, which I have drawn below, is a strongly regular graph with 50 vertices, regularity 7, 0, lambda 0 and mu 1. Now, lambda is 0 means any two adjacent vertices will not have a common neighbor. So, no triangles are formed in the graph. So, strongly regular graph with lambda is equal to 0 implies that G is triangle free. Now, when you look at lambda is equal to 0 and mu is equal to 1, they belong to a wonderful class of graphs called Moore graph. If you Google Moore graph, you get a lot of things, and I've written one of them for surprise. A basic question of Moore graph is whether there exists a strongly regular Moore graph of order 3250, regularity 57, 0, 1. So, does there exist a strongly regular graph with parameters 3250, 57, 0, 1 is still a problem. Those who are interested, you can refer to Moore graphs in the Wikipedia. Now, I want to pay a tribute to J.H. Conway, who passed away on 11th April 2020 in USA, a British mathematician, due to corona, very unfortunate part. He has a problem called Conway's 99 graph problem. Does there exist a strongly regular graph with parameters 99, 14, 1, 2? So, pay homage to J.H. Conway, who asked this, who could not see the solution of this. We still don't know whether there exists a strongly regular graph of order 99, 14, 1, 2. Okay. The parameters of strongly regular graphs cannot be, lavishly we cannot take, not for all values of k and mu and lambda. So, it should satisfy a compatibility relation n minus k minus 1 into mu is equal to k into k minus lambda minus 1. The complement of a strongly regular graph is also strongly regular with parameters n, n minus k minus 1, n minus 2 minus 2k plus mu, and n minus 2k plus lambda. And you can easily see that complement of Shrikhande graph is a strongly regular graph with parameters 16, 9, 4, 6. Now, look at L2M. L2M, capital M is a set of M numbers 1, 2, 3, etc. M. I'm considering graph L2M, which is having a vertex set M cross M, Cartesian product of M and M, and two vertices are adjacent if the first coordinates or second coordinates are same. So you can consider this as a graph on the cells of M by M chessboard. 1, 2, 3, etc. M on the top and 1, 2, 3, etc. M on the row. For example, you will have 1, 2, 3, etc. 8, usual 64 chessboard. And two cells are adjacent if they are in the same row or column. I suppose, the definition of L2M, because this is crucial in the next slide, which gives birth to Shrikhande graph actually. So L2M consists of vertex at M by M, and two vertices or two cells are adjacent if they are in the same column. We can easily prove that it's a strongly regular graph with parameters M square, 2 into M minus 1, M minus 2, and 2. So L2M graph is a strongly regular graph with parameters M square, 2 into M minus 1, M minus 2, and 2. Now comes the famous Shrikhande theorem, which gave birth to Shrikhande graph. So let G be a strongly regular graph with parameters M square, 2 into M minus 1, M minus 2, 2. Then G is isomorphic to L2M except when M is equal to 4. When M is equal to 4, let the parameters become 16, 6, 2, 2. And you know, L2M is not the L24 is not the only graph with these parameters, and the exceptional graph is now called Shrikhande graph. So there exists a pair of non-isomorphic graphs with the same parameters with parameters M is equal to 4 and parameters M square, 2 into M minus 1, M minus 2, 2, which comes out to be 16, 6, 2, 2. And the two graphs are L2, 4 and Shrikhande graph. Shrikhande graph is, so Shrikhande showed that L24 is not the only graph with these properties, and there is one more graph now called Shrikhande graph. In fact, the Shrikhande graph was the logo of two of the international conferences organized in CUSAT, one in 2010 as a satellite conference of the International Congress of Mathematicians, for which I was the convener. And my students, research scholars and master students arranged a farewell conference 2 years back, ICRTGC 2018, wherein also the logo was Shrikhande graph. It came to a surprise for me because I've just met Shrikhande only once, that too about 20-25 years ago at Bombay University. We have never corresponded. I was fortunate to hear his feeble voice when I talked to him over phone. Thanks to Sharat Sane for giving his AIDS number. That's all my relationship with Shrikhande. But somehow I felt that Shrikhande graph should be a logo which is purely an Indian graph. So let me take 5 minutes more and conclude. How are you going to characterize the strongly irregular graphs? A graph G is strongly irregular if the adjacency matrix A satisfies the equation AJ is equal to JA is equal to KJ. J is all one matrix, and A is the adjacency matrix of a graph. You know, the adjacency matrix of a graph is height entry is 1 if Vi and Vj are adjacent, and it is equal to 0 adjacent. So a graph becomes strongly irregular if and only if Aj is equal to Ja is equal to Kj, and A square plus mu minus lambda A plus mu minus K into I is equal to mu of J. So these two relations characterize a strongly irregular graph. Now, if you look at the spectral analysis of strongly irregular graphs, this becomes another characterization. A graph is strongly irregular if and only if its eigenvalues, they have 3 distinct eigenvalues, K, and the other 2 are given by 1 by 2 lambda minus mu plus or minus root of lambda mu square plus 4 into K minus mu. So I gave you 2 characterizations of adjacency matrices. Now, graphs whose all eigenvalues are integers, they are called integral graphs. And which graphs have integral spectra turns out to be an open, difficult problem. Okay, so determining which graphs are uniquely determined by their spectra is a very difficult problem. But we have at least seen that Shrikhande graph is not determined by its spectrum because there is also another graph L24 which has the same spectrum as Shrikhande graph. So Shrikhande graph is not uniquely determined by its spectrum, but there are some graph classes which are uniquely determined by its spectrum, but finding a solution for a generic graph is difficult. Now, I'm slowly coming to the end of my presentation. I will list out plenty of properties of Shrikhande graph, and many more properties are still to be found. It's an Eulerian graph, which is obvious because regularity is 6. It is a graph, all its spectrum are integers. Spectrum is 6 to -2 with multiplicity 169. Chromatic number is 4. Girth is 3. Therefore, your Shrikhande graph is not bipartite. It is Hamiltonian. Edge connectivity is 6. Means to disconnect Shrikhande graph, I have to remove at least 6 edges. Diameter and radius are 2. Therefore, it is a self-centered graph. Each vertex is a center. Independence number is 4. Now, it's a strongly regular graph. The lambda is equal to mu is equal to 2 means that this graph is associated with a symmetric, balanced, incomplete block design, a special type of design from design theory. Shrikhande graph is a Cayley graph, whereas Peterson graph, which is another strongly regular graph, is not a Cayley graph. But still, we don't know what is the chromatic polynomial of Shrikhande graph. That is, number of different ways of coloring a graph using lambda colors is actually a polynomial called chromatic polynomial. And we still don't know the chromatic polynomial of Shrikhande graph. It is not planar, means I cannot embed Shrikhande graph in a plane, but there exists a surface which is torus, on the surface of which I can always embed planar graph, Shrikhande graph, in the sense that I can draw Shrikhande graph on the surface of a torus such that there is no crossing of edges. Its automorphism group is of order 16. You'll be happy to see that the book of combinatorial matrix theory by Brualdi and Ryser contains the Shrikhande graph as its facing cover. And our research group in Cochin studies a lot about the distance spectrum. You can find that the distance spectrum of Shrikhande graph is 24 minus 4 0. There are many other properties of Shrikhande graph which is not mentioned here or people don't know. So those who are interested can concentrate on Shrikhande graph and look at many more properties as an exercise. You can get a dig graph out of a Shrikhande graph as mentioned. It's a symmetric graph on 32 vertex, but dig graph is determined uniquely by its spectrum, whereas Shrikhande graph is not determined uniquely by its spectrum. So I am winding up with references to very good books on orthogonal Latin squares based on groups, and book of combinatorial designs, a book on Latin squares. Those who are interested to work in these types of mathematics, you are welcome to correspond with me. Of course, I am not an authority on Latin squares or even any branch of mathematics. Mohan, Shrikhande, Sane, they have all worked in strongly regular graphs and design theory. Now, I will show four persons. In fact, I was very sorry or sad to add Shrikhande's photo in that group. These are all mathematicians who lived more than 100 years. Vietoris, Vietoris is a great topologist. He has another distinction that he gave an invited lecture in his own 100th birth anniversary, very surprising and lucky. You have DJ Struik, who is a historian of mathematics on the right side. Below, you have a great number theorist, R.K. Guy, who also lived more than 100 years. And we have now another great mathematician, Sarath Shrikhande, who passed at the age of 102. Again, a great mathematician who lived more than 100 years and served the country and mathematical community. So my special thanks to Sharath Sane, my good old friend from University of Mumbai and currently at CMI Chennai. Another friend, C.S. Aravinda, Tata Institute of Fundamental Research, Center for Applied Mathematics, Bangalore. Mohan Shrikhande, in fact, he wrote an article to my pre-conference proceedings of ICRTGC 2010, Euler's conjecture and the Shrikhande graph. And also thank Peter Cameron for his blog on ICRTGC 2010. In fact, he gave a presentation in an earlier version of this conference, this webinar in another college. In fact, Peter Cameron also sent me a lot of materials for preparation of this. And my good friend, another friend, Arun Muktibodh, who has a video film on Sarath Sharat Sane. This we will be showing very soon. So I'll be happy to show the pictures. Of course, Mohan Shrikhande is with us. Peter Cameron, Sharat Sane, Mohan Shrikhande, and Aravinda. I thank Srimati Bridget Gigi, Principal of Aquinas, and Zita Paul, HOD, my proud former students, and Dr. Tarana, the coordinator IQAC, and all these lockdown period, my wife Prema, Shruti, and son-in-law Sandeep were also helping me prepare these slides. And I have a message, in the age of the current lockdown, Corona is creating a trouble. So break the chain, don't leave, wash your hands always. And I thank all the members, all the fellow mathematics research scholars who attended this webinar. This is my 4th webinar. Students who arranged all these things during these last 2 months, and wish you very best in life, and thank you very much.
Okay, sir. Thank you. Thank you very much. I think we can move to the video now. In between, participants can ask their doubts in the chat. So
Yes.
you can read that. So this is actually a 30 minutes plus video. We will not be showing the entire thing, but just a glimpse. After that,
Yes.
I will be sharing the Google Drive link for that. So the
Yes.
participants can see so their own ways. Okay. Okay, fine. So I think we can conclude this session. I invite Caroline is there. Right? If Caroline is there, Caroline can come and have a word of thanks.
It's my privilege to have been asked to propose a vote of thanks on this occasion. I, on behalf of the Mathematics Department, extend a very hearty vote of thanks to our Honorable Speaker, Dr. Ambat Vijayakumar Sir, who spared time for gracing this webinar. The way he introduced the great mathematician S.S. Shrikhande and explained his works is exemplary. Thank you, sir, for making this webinar so meaningful and very informative. I express our profound gratitude to Dr. Mohan S. Shrikhande for his valuable presence in this webinar. I express my gratitude to our respected manager, Reverend Father Johnson Charamal, for providing encouragement for conducting this webinar series. I also express my gratitude to our respected principal, Ms. Bridget Gigi CJ, for her moral support and valuable presence. I would like to thank our respected vice principal, Dr. Joseph Justin Ribello, for all his words of wisdom that radiated a source of energy within us for conducting this webinar. Thank you, sir. I would like to thank our beloved HOD, Ms. Zita Paul, for her valuable guidance and selfless support and work for making this webinar a great success. Thank you, ma'am. A webinar series of this dimension cannot happen overnight. Surely it requires a great planning and bird's eye for detail. It's really an appreciable initiative taken over by the IQAC team. So I'm grateful to the IQAC team for giving us the opportunity for conducting this webinar. I especially thank the technical arrangement team and my colleague Mr. Raju George Michael, who have been the backbone of this webinar. Finally, I express my deep gratitude to all the participants for your valuable presence and cooperation. Thank you.